Hello, welcome to the last lecture video of Chapter 10. Hope you're doing okay with this stuff so far, because the last section here is all about putting it together. So what you're going to want to do is turn to page 20 in your note sheets, which can be found under handouts on my math lab if you haven't downloaded them for this chapter yet. And the idea here is for all of you to practice picking out the correct technique. So whether that's using one prop Z test, or that's using T test, or it's using one prop Z interval, or it's using T interval, or it's using binomial probability if you have a small sample size with proportions, or if it's using StatCrunch if you have a data set. That's what this section is all about, is being able to do a hypothesis test, but also being able to pick the right hypothesis test. So what I'd like you to do is go ahead and flip to that page in your notes and get started going through these problems. So what I'll do to start out here is, if you don't have them printed out, I'll flip through them slowly enough that you can pause on each page and try these. And then once I've given you a chance to try all of these, you can go through them. So here we go. Okay, so now that you've all had a chance to pause the video and try these, let's go ahead and just run through all of them together, just so you can see a few more examples before you work on this last homework assignment and the quiz for Chapter 10. So the first one says, in October 1945, the Gallup organization asked 1,487 randomly sampled Americans, do you think we can develop a way to protect ourselves from an atomic bomb in case other countries tried to use them against us? With 788 responding yes. Did a majority of Americans feel the United States could develop a way to protect itself from atomic bombs in 1945? Use alpha equals 0.05 level of significance. So this is similar to one of the problems we ran into in our notes for section 10.2. So notice we're getting a number of people out of a total number, so that's a proportion. And it says, did we think a majority of Americans? Well, a majority, remember, is more than half. So our null hypothesis is going to be half, so p equals 0.5, and our alternative hypothesis is going to be a majority, more than half. Okay, so we're dealing with p, so that means we're going to use one prop z test. Okay, and when we do one prop z test, remember we're giving our p value, which in this case is 0.5, our x value, which is 788, and our n value, which is 1487. Okay, so go to the ClassCalc app, put in stat test 1 prop z test, and put in these values. So 0.5, 788, and the last one was 1487. And so when we do that, we're doing the greater than one, so that's the 0.015, the lower left answer. So our p-value here is 0.0105, and so that is less than alpha. So therefore, we would reject H naught, which means we could say there is sufficient evidence to suggest the alternative hypothesis, which in this case is there is sufficient evidence to suggest that a majority of Americans thought we could find a way to protect ourselves. Okay, and so that's the idea. And as we go through the rest of these, I probably won't write all of them out to this level just to make this video a little shorter, but this is the kind of detailed conclusion we're looking for. Okay, so the second one here says the manufacturer of toner cartridge claims the mean number of printouts is 10,000 for each cartridge. A consumer advocate is concerned that the actual mean number of printouts is lower. He selects a random sample of 14 such cartridges and obtains the following number of printouts. So we can start by writing our null an alternative hypothesis. So he thinks the mean number is lower, so the manufacturer says that it's 10,000. So mu equals 10,000, and he thinks mu is less than 10,000. Okay, and so now, because we have a data set here, we're probably going to want to use StatCrunch. Although you could use ClassCalc and just type in all those data values. But I'm going to use StatCrunch because I already have it put in. So I'm going to go to StatCrunch. And that's our printer data right here. So I want to do the first thing I have to do is make sure I can do a hypothesis test. So I want to do a QQ plot for normality. So I'm going to graph QQ plot. And I'm going to choose to do it for printer. And I'm going to choose the normal quantiles on the y-axis. And so if we do that, you can see that that's pretty close to straight. That's pretty close to a linear. So that's good. So that part works. And then we want to do the box plot. So I go graph box plot for printer. And I choose use fences to identify outliers. Leave that alone. And I can hit compute. And there are no outliers, right? Because we don't have any dots. So that's good too. So for this first part of this question, we can say the conditions are met because the QQ plot was approximately linear. So the data is approximately normal. And the box plot had no outliers. Okay, and so now we can do our hypothesis test. So in the calculator that looks, in StatCrunch that looks like this, right? We hit stat. We use T-stats, one sample with data. We choose which column we're working with, which in this case is printer. And then we put in our mu, which is 10,000. And we put in our inequality, which in this case is less than. Okay, and we can hit compute. And we get a p-value of 0.1012. So p equals 0.1012, which is not less than alpha. So we do not reject H naught, and therefore there is not sufficient evidence to suggest that the mean number of printouts is less than 10,000. Okay. The next one here, in 2001, the mean contract interest rate for conventional 60-year first loan for purchase of a single-family home was 6.3%, according to the U.S. Federal Housing Board. A real estate agent believes that interest rates are lower today and obtains a random sample of 41 recent 30-year conventional loans. The mean interest rate found was 6.05, with a standard deviation of 1.75. Is this enough evidence to conclude that interest rates are lower at the alpha equals 0.05 level of significance? So when you go to write this one, notice that we're using percentages, but it uses the word mean. So here, this is actually an average percentage, not a proportion. So when you do this, even though it gives you a percentage, that would normally use P, but the word mean here tells me that this is actually a mean. So our mean is 6.3. And I don't change it to decimal because it's a mean. It's not a, we're not treating it as a proportion. So mu would be 6.3. H1 would be that mu is less than 6.3 because we think they're lower now. And then because we're dealing with the mean, we're going to do a t-test. And when you do a t-test, you put in the mean, the standard deviation from the sample. Sorry, I forgot part. So first, you put in the population mean you're working with. So that's the 6.3, the mu. Then you put in the sample mean, the sample standard deviation, and the sample size. So in this case, 6.3, 6.05, 1.75, and 41. Okay, so we can do stat, test, t-test, and then we put in the data we just said. So 6.3, 6.05, 1.75, and 41. When we do that, we get all three answers and the test statistic. And we thought it was lower, so that would be 0.1829. So our p-value, 0.1829. And so that is not less than alpha. So we do not reject. And we could say there is not sufficient evidence to suggest that the mean interest rate is lower than it was, lower than 6.3%. Okay. Okay. So on the next page, same idea. So does playing Mozart for unborn babies result in children with higher IQs? A psychologist obtains a random sample of 20 mothers in her first trimester of their pregnancy. The mothers are asked to play Mozart in the house at least 30 minutes each day until they give birth. After 5 years, the child is administered an IQ test. We know that IQs are normally distributed with a mean of 100 and a standard deviation of 15. If IQs of children in the study result in a sample mean of 104, is there evidence that the children have higher IQs? So in this case, there's a really important part here, which is that we know IQs are normally distributed. That means it's okay that our sample size is less than 30, which is normally what we're looking for. So our H naught here is that mu equals 100, and H1 is that mu is greater than 100, and we can do a t-test. So when we do a t-test, we put in our mean, our population mean, which is 100, our sample mean, which is 104.2, our standard deviation, which is 15, and our sample size, which is 20. Okay, and so when we do this one, so 100, 104.5, 15, 20, and we're doing greater than, so that's 0.0978. So P equals 0.0978, which is not less than alpha. So we do not reject H naught. So we can say there is not sufficient evidence to suggest that that playing Mozart for babies raises their IQ scores. Okay. The next one says, according to the Insurance Information Institute, the mean expenditure for auto insurance in the United States is $774 in 2002. An insurance salesperson believes that the mean expenditure for auto insurance is different now. He obtains a random sample of 35 auto insurance policies and determines the mean expenditure to be $735 with a standard deviation of 48.31. Is there enough evidence to conclude that the mean expenditures for auto insurance is different in 2002 at the 0.01 level of significance? Okay, so this is going to be pretty similar to the one above. H naught is mu equals 774. H1 is different. He wants to know if it's different now. So mu does not equal 774. And we can do a t-test. So that's 774, the population mean, comma, our sample mean, which is 735, our sample standard deviation, which is 48.31, and our sample size, which is 35. And the reason we can do this with a t-test is because our normal distribution is greater than 30. So we go into our calculator, just like the one before, and we put in the given information. So 774, 735, 48.31, and 35. And in this case, we think they're different, so we're using the bottom right one. So 0.0000 is what we get when we round to 4 decimal places. So P equals 0.0000. Okay. Just checking to make sure I put the data on right. So that is less than alpha. So we would reject H naught, and we would say there is sufficient evidence to suggest that the mean auto insurance policy is different today than it was in 2002. For the third one here, in 2001, 23% of American university undergraduate students had at least one tattoo. A health practitioner suspects that the percent has changed since then. She obtains a random sample of 1,026 university undergraduates and finds that 254 have at least one tattoo. Is there sufficient evidence to suggest the proportion is different from 0.23 at the 0.1 level of significance? Okay, so this time we're dealing with proportions, right? They didn't use the word mean anywhere. So this would be P equals 0.23, and we want to know if it's changed, so that's P does not equal 0.23. We're going to do a 1 prop Z test, and we're going to put in P, so 0.23, X, which is 254, and N, which is 1026. Okay, so stat, tests, 1 prop Z test, 0.23 is P, X was 254, N was 1026. Okay, and so if we're doing a change one, that's 0.1813. Okay, and since we are doing it for not equal to, that is not less than alpha. So therefore, we do not reject H naught, and we say that there is not sufficient evidence at the to suggest that the percentage of university undergraduates has changed who have at least one tattoo. Okay, so that's the idea. Okay. And then the last page of our notes. So a certain vehicle admission inspector station advertised that the wait time for customers is less than 8 minutes. A local resident is skeptical and collects a random sample of 49 wait times for customers at the testing station. He finds that the sample mean is 7.34 minutes with a standard deviation of 30.2 minutes. Does the sample evidence support the resident's skepticism? Okay, so we could say that H naught is mu equals 8 minutes and H1 is mu is less than 8 minutes. And so then we're going to do a t-test. And we put in mu, which is 8, our x bar, which is 7.34, our s, which is 3.2, and our sample size, which is 49. And we plug that into class calc, into the t-test. So stat, test, t-test. We got 8, 7.34, 3.2, and 49. And so for less than, we got alpha equals 0, P equals 0.0777. So P equals 0.0777, which is not less than alpha. So we would do not reject H naught, and we would say there is not sufficient evidence to suggest that the mean wait time is less than 8 minutes. Okay, and then for the last one, with a previous contractor, the mean time to replace a street light was 3.2 days. A city councilwoman thinks that the new contractor is not getting the street lights replaced as quickly. She selects a random sample of 12 streetlight service calls and obtains the following times to replacement. So what we want to know is, first of all, can we do this? But then the hypothesis test we're going to test is that is mu equal to 3.2 days or is mu greater than 3.2 days? Is it taking them longer to replace the streetlights? So because this is data, I would highly recommend using StatCrunch again. So I already have that data here in my StatCrunch. And so first thing I want to do is make sure that I can do the test. So I want to hit graph, do a QQ plot, normal quantiles on the y-axis. Sorry, I forgot to select streetlights up in select column. Hit compute, and that's approximately linear, so that's good. And then we want to do a box plot for streetlights. We compute, and there's no outliers. There's no dots beyond the whiskers, so that's good. Okay, so we can go back here into our notes, and we can say the conditions were met because the QQ plot was approximately linear, which means the data is approximately normal. And the box plot had no outliers. Okay, and so now we can do our hypothesis test. So in StatCrunch, we go to Stat, T-Stats, one sample with data. Choose the data you want, which is streetlights. Put in your hypothesis. So my hypothesis is that mu equals 3.2. And I want it, my alternative is that it's greater than 3.2. And we hit compute. And we get a p-value of 0.0361. So p equals 0.0361. So that is less than alpha. So we reject H naught. So there is sufficient evidence to suggest that the time it takes the new contractor to replace streetlights is greater than 3.2 days. Okay, so that's it for section 10.4. I hope all these extra examples are helpful when you go to do the homework and the quiz. Don't forget to do your homework and the quiz online. And if you have any questions, feel free to call, text, or email me. And also look out for virtual office hours.